Okay, so then I think we can start. So welcome all, remote and person here.
Which is this guy? Yeah.
It's my great pleasure to have Sweet Ibrahim from the University of Victoria in British Columbia, Canada, talk to us about revisit singularity formation for the inviscid primitive equations. Thank you, Sweet.
Thank you very much, Anna. Thank you for this kind invitation, and on behalf of you, so to all the organizers, I'm so pleased to give this talk, and wish that it would be in person, but maybe another time. So I think I will be in the institute next April for another workshop. So today we'll talk about a recent joint work with Chuan Lin and Charles Collot. But before going to that, I would like to give a short survey about this primitive equation and the singularity. And for instance, I will review the previous singularity formation results, two results that I will mention, and then I will explain why there was a need to revisit them. And then I will share with you my recent results, as I said. So,
Can you put it in the full screen mode? It's a little small for us.
Oh, I see. Sorry.
Sure.
This is the good notes.
You are on the iPad. Okay, never mind.
I'm on the iPad. I'm sorry because
it's fine. It's fine.
Yeah.
Thanks.
So these are two works that involved the collaborators. So from the past, Idris, of course, and Tsao and Nakanishi for the previous singularity result, and then more recently with Charles Collot and Chuan Lin. So as I said, this is an overview of my talk. The plan is to walk you through the derivation of these primitive equations and why they are important. And then I will try to explain what is the situation in terms of global regularity, singularity formation when we compare it to Navier-Stokes. So that's why I would like to briefly recall what are the known results in the viscous case. And then I will specify my setting for this talk about the 3D inviscid primitive equation, and I will be more precise in terms of assumptions and symmetries and so on and so forth. So once we define the setting for the inviscid case, so I will review the known results about well-posedness, ill-posedness, and blowup. And I'll try to explain also the idea of the previous two results that I know about the singularity formation, and then try to comment why we need to revisit them, as I said. So the last part of my talk will be for the proof of the new result. So first I will construct new self-similar profiles, and then I'll study the stability and mention the results. And at the end, so I will give you the elements of the proof. Good. So the primitive equations were derived from the very well-accepted model that is Boussinesq equations. So let me try to remind the Boussinesq equations. So this consists of two equations or three on the velocity field of a fluid. So U is normally 3-dimension or 2-dimension. We can set it, this Boussinesq equation on a domain D, a special domain D, across the time. And the domain D can be periodic, can be the whole space, infinite channel, or other types of domains. Okay, so here we have few parameters in this momentum equation. So we have the viscosity. So the density, the mass density here, it's supposed to be constant. But we have the viscosity, and we have the Coriolis force and the gravity. And this momentum equation is coupled with the heat transport diffusion equation on the temperature T. K here is the vertical vector. So it's coupled with the temperature T, and the fluid is assumed to be incompressible. And this temperature, so it may involve some diffusivity constant kappa. Okay, so this is the full set of Boussinesq equation. And as I said, this is well accepted model in atmospheric and ocean science, in industry also, cupboard ventilation, and so on and so forth. Now, so these applications include different models, and depending on the model that you want to study, you may go a little bit further and try to reduce or simplify the full Boussinesq equations. And this is the context of atmospheric models, for instance, or models of in the ocean. So if we observe here the circulation, the flow circulation in the oceans, and we want to study this using the Boussinesq approximation, then we can see here that there is a difference between the horizontal scale and the vertical scale. So the horizontal scale can go to a few thousand of kilometers, while the vertical scale, which is the depth of the ocean, can be like a few kilometers. So considering that, then it makes sense to study the vertical and horizontal motion separately. And what I have done here is nothing but rewriting the same Boussinesq equations, but here I split the horizontal motion and the vertical motion. So the velocity vector field U here, it consists of the horizontal velocity, and W is the vertical component of the velocity. And as you can see here, I went further and split the viscosity by distinguishing the horizontal viscosity with the vertical one. And I did the same thing for the diffusivity here. So this is the horizontal diffusivity, and this is the vertical one. Okay, so I just want to study or analyze what happens when we study large-scale models. What happened to these equations? Okay. So now, to be more rigorous, so we can base it on the actual data of the horizontal viscosity and the vertical viscosity, diffusivity, and so on. So physically speaking, so the vertical viscosity is much smaller than the horizontal one. Okay. And as I said, the vertical scale is much smaller than the horizontal one. So, so Azirar, Guyen, and Li and Titi quite recently, so they rescaled the viscosity, the vertical one, with by introducing this parameter epsilon, which is depth versus the horizontal length scale. Okay. So by choosing this ansatz and rescaling the horizontal velocity in the z-axis, in the z direction, right? So now the z is between 0 and 1, so epsilon z is between 0 and 1. So this is the thin domain. And you do the same thing to the vertical velocity and the temperature and the pressure. Okay. Now the domain is rescaled to z between 0 and 1 instead of thin domain, 0 and epsilon. And once you introduce the scaling, then the resulting equations can be rewritten in this form. And what we see here is the factor of epsilon squared that appears on the vertical component of the acceleration. Okay, so this is the acceleration, this is the vertical component of the acceleration, and then we see this epsilon squared that pops up. And then, so this is a formal computation. And this formal computation suggests that at the limit, so the gradient, the vertical gradient of the pressure should be balanced by the temperature. And this is known as the hydrostatic balance. Okay. Okay, so this is the formal limit. When you take epsilon go to 0, then formally what we get is the very famous primitive equations. Okay, with all the parameters, Coriolis and the viscosity. Good. So this formal computation was, as I said, first carried by Azeral Guyen, and then more recently by D and TT. Good. So one thing to observe here is that there is no equation on the vertical component of the velocity. So there is no dynamic that governs the motion of W. Okay. Instead, the W, the vertical component of the velocity, is slaved by the incompressibility of the fluid. So W can be recovered by integrating the incompressibility condition, and there is no dynamic of it. And this observation really made the analysis of these primitive equation quite challenging in terms of well-posedness. Why? The reason is because of this. So there is a loss of one derivative in the W, in the X derivative. Okay, so these are the full set of primitive equations when we consider viscosity and diffusivity, and they were derived from, as I said, the Boussinesq approximation using dimensional analysis. Good. So let me now survey a little bit the main results. And I apologize because this list literature, so it's not exhaustive, and I'm very sure I missed many references, and I apologize for that. But I will mention the most important results. So when we have full viscosity, then there is the striking result in this direction is by Tsao and TT in 2005, where they showed the global regularity. So there is no singularity when we have full viscosity. And the existence and uniqueness was done in the scale of Sobolev spaces. And then with different boundary conditions, Kobelkov in 2006 and Kukavica-Zian 2007, they used different boundary conditions. And more recently, Hiber and Kashiwabara, so they used LP theory and semigroup theory to establish the global regularity. Now, when you relax these conditions on the diffusion, so if you assume that you have only horizontal diffusion, and you may let the vertical diffusion to be 0, which is physically the most relevant case. So the global existence was established also by Tsao, Li, and TT. Now, this equation, when we take horizontal viscosity to be 0, but with vertical viscosity, it might be allowed, then this primitive equation is sometimes called the hydrostatic Navier-Stokes equation. And if the vertical viscosity is 0, it's called hydrostatic Euler equation. Okay, so if we don't have horizontal viscosity, so remember what I've said earlier about this loss of derivative, then all kinds of instability can basically happen. So Renardi, he showed like there is ill-posedness in the scale of Sobolev spaces. And with small initial data, which is analytic in the horizontal direction, not in the vertical direction, then more recently, Paiku, Zhang, they established the global well-posedness for small data in the 2D case. Okay, so it seems like because of this lack of loss of derivative, so clear we cannot solve in the scale of Sobolev spaces particularly in the horizontal direction. And the space of analytic functions would be the most suitable to establish well-posedness. Good. Now, if we ignore now the rotation, so this is not the focus of this talk, then the inviscid primitive equation is this set of equations colored in red. So this is the momentum equation. U now is the horizontal component of the velocity. It's U1, U2, or U and V. And W is the vertical component. And as I said, it's slaved by this incompressibility condition. Okay. So now this is the setting that I will fix from now on. So we will mainly focus on this set of equations. And we'll take a domain M that can be split into two pieces. So this is the horizontal one. So X and Y is in M, and Z is between 0 and 1. And M is a smooth bounded domain with real analytic boundary. Okay. So now we supplement this inviscid primitive equations with the physical conditions. So the vertical velocity, it's 0 on the top and at the bottom of the domain. Z equal to 0 and Z equals to 1. And the second boundary condition is that if you average the horizontal velocity dotted with N, you average it with respect to Z, then you get 0. Okay. So this is the second boundary condition. And now this system, as I said, this is called the hydrostatic Euler's equations. Good. So this is the main target of our analysis. And I did this introduction just to compare with Navier-Stokes versus Euler's equations. So Navier-Stokes, we don't know the global regularity yet. Though for the primitive, whenever we have horizontal viscosity, then we do know the global regularity. And for the inviscid Navier-Stokes, which is Euler's equations, so the problem of formation of singularity for smooth solutions, it's still open, and we will see what's the counterpart for the inviscid primitive equation. And that leads me to this case. Okay. And another thing, if I want to summarize also the case of viscosity, partial viscosity, I think the only remaining case is when we have vertical viscosity. Then we don't know if singularity can appear. Good. So for this inviscid primitive equation, so we know linear and nonlinear instability. So this has been proved by Renardi back in 2009. Han Quan and Nguyen in 2016, they proved the nonlinear instability. And in the case of rotation, so if you add the rotations, this is together with Chuan Lin and Idris, we showed that they are ill-posed in the scale of Sobolev spaces. Now, this is in terms of instability. Now, in terms of singularity, so there are two results that I know. So the first one by myself with the Tsao and Nakanishi Titi in 2012. And the second one by Wong 2 weeks later after we posted our paper on arXiv. So these are the two results, and the most recent one is with the Lin and the Titi last year, where we added the rotation. Okay, so there has been shown formation of singularity for the primitive inviscid primitive. Okay, now in terms of well-posedness, as I mentioned by the result of Peiku Zhang. So the most suitable space to study well-posedness is not Sobolev for sure. And it would be the space of analytic functions. And this what has been shown by Kukavica, Timam, Vikolzian in 2011 in a very nice paper. And that has been generalized by myself, Lin, and Titi when we add the rotation. And in addition, we studied the effect of the rotation on the lifespan. Okay, so this is if we don't assume any symmetry condition on the initial data, if you want. But there is another type of result about local well-posedness by Masmoudi and Wong from 2012, where if you assume some convexity condition on the initial condition, then they were able to show the local well-posedness in the scale of subordinate spaces. Good. So now let me be more specific, and I will focus on the finite time blow up for solutions to the inviscid primitive equation. So I will summarize these two works, this one and this one, give you, roughly speaking, the idea of the proofs, and then a few comments how to proceed after that. So, so my result with Tsao, Nakanishi, and Titi, it states like there exists a smooth initial data for which the corresponding smooth solutions blows up in finite time. Okay. And the result by Wong, seemingly very different, but I will show you that they are not, indeed, they are not very different. So he was able to construct an initial data. So he's assuming that there is a point x hat, which we can assume to be 0 actually. And there is, so there is a point x hat for which if you fix the velocity at this point, then the velocity is independent of on the z variable. Okay, so this is that. And then he assumed that convexity condition or concavity condition on the x derivative of this initial data. So if you take the x derivative of the initial data, so it has a critical point at this point x hat z equal to 0. And this means that it's concave down at the point x hat in terms of z. Okay, so if you take this initial data, then you can, and if you assume a priori that the solution does not blow up in the infinity norm, nor the pressure blows up in the infinity norm. In other words, the acceleration does not blow up also. Then he can construct so he can show that the x derivative, it goes to minus infinity along a trajectory. So capital X here is the characteristic from this point x1 at z equal to 1 at the boundary, top boundary. Okay, so so let me sketch the proofs of these two results and then give some comments. So the first step in my result with the Tsao, Nakanishi, and Titi. So we started with the 3D or 2D primitive equation, and we did some symmetries. So we work in a class of symmetries of solutions. So let's look to the odd symmetry in the X and even with respect to the pressure, and even with respect to the vertical velocity. So this symmetry with this boundary condition, this physical boundary condition, it's preserved by the flow of the primitive equation. Okay, and here, let's assume like the V component is 0 and it stays 0 for all time. Okay, so the idea is to reduce the 2D to a simpler one-dimensional PDE. Okay, for which we can show formation of singularity. Okay, so the next step is to solve for the pressure. So the pressure is the non-local term, and working in this class of solutions, then we can indeed solve for the pressure in terms of the velocity vector field. And more precisely, we can show that the x derivative of the pressure is given by the average of UUX, the Z average. Okay, now once we have the pressure, we can substitute it back into the equation. Okay, the primitive equation. So the primitive equation will give us this PDE. And now if we restrict it to the axis, x equal to 0, so we get a closed equation on the x derivative or the z derivative of w. The x derivative of u is balanced by the incompressibility by the z derivative of w. Okay, so we get this blue equation, this one-dimensional PDE, and the boundary conditions are 0 at the top and at the bottom. Okay. Then we observed this reduced model, and it has a scaling. For instance, if you change w by lambda w, then the equation remains unchanged. And this suggested to find an ansatz that blows up in this form. Okay, so at time t equal to 0, it's some function that depends on z, and it blows up exactly at time t equals to 1. And this is the boundary condition on w. Okay, so when we substituted this ansatz into this reduced model, so we got the profile equation 13. Okay, and there was a parameter here. This parameter m, it's not an arbitrary parameter. It's slaved by the conservation of the L2 norm of WZ square. If you take, if you average, then you get this is an arbitrary. Good. And it turns out that this equation has infinitely many profiles, and we showed that. And these profiles, they are in the C alpha class. So the second derivative has alpha m regularity, and alpha m is explicitly given by this number. Okay. Now, one observation is that this blue PDE, you don't see any loss of derivative anymore because of the restriction on the axis. And therefore, you can show the local well-posedness in the scale of Sobolev spaces H2. Okay. So that was our proof, and let me sketch Wong's proof here. So Wong's proof assume that the pressure, as I said, the gradient of the pressure, which is the acceleration basically, and the L infinity norm of the solution, they don't blow up. So you do have a bound. Then you can use Galilean invariance to centralize this. To centralize this x dot to 0 and this value of u hat to be 0. You can assume them 0 indeed. So that's what he called the freezing lemma. That's exactly this lemma, where you can freeze the value of x and then you hat to 0, 0. Okay, so this is the first step. And the second step, remember, his condition on the initial data was concavity condition. So dxu0 is a concave function in terms of the z variable. Okay, and using this freezing lemma, he was able to show that if you had that initially at time t equal to 0, then you can propagate it for all time. Okay, so that's good. And once he propagates that, so there is a nice calculus inequality that basically tells you how to get rid of the pressure. So this is, remember that this integral is related to the pressure basically. So you can re-express this or estimate this by a velocity term in some sense. And once you use this nice calculus identity using this convexity property, then you get the Riccati type differential equation, and you know that it has a finite time singularity. Okay. So this is the proof by Wong. So let me say a few comments here. So now, how to lift these results to the two-dimensional or three-dimensional primitive equation. So using our profile phi m, so we can construct initial data, which looks like this, with the vertical initial velocity. And we know that if there is a smooth solution to this initial data, then it has to blow up in finite time. Okay, that's what our result says. The second result is by Wong is in some sense better than our, in the sense that you can choose analytic data. Okay, you can choose analytic data that satisfy Wong's condition. Okay, you can construct them explicitly. So for instance, if you choose this one, so the advantage is that you can apply the local well-positiveness. So for that initial data, the 2D or the 3D problem have only one solution, right? And now you know that something happened to that solution. So that's Wong's result. Because remember, Wong's result says, it doesn't say like there is a singularity, but if you have an a priori bound on the velocity, if the velocity does not explode, nor the acceleration, right? Then you can find the trajectory for which the derivative goes to minus infinity. Okay, so so something happens, but it's not clear what exactly happens. Okay, so this is the first observation, and that was the need why we wanted to revisit this singularity formation for the primitive equation. So the second observation is, as I said, we can give explicit examples, and in the paper with Lin and Titi, so we constructed this, and we showed like the time of existence. It's of this order. Lambda is an arbitrary parameter, positive. And now here the second observation. So if you average with respect to z this initial data, okay, you get 0. If you average in z this initial data, you get 0. And this is not surprising in the sense, in the following sense. So you can rewrite the primitive equation. So sorry to bring you back a few slides here. I'm sorry. Yeah, here. So if you go back to the primitive equation, you can rewrite this equation 4 in terms of two equations on barotropic component and baroclinic component. What does this mean? So the vector field u, you can decompose it into u bar, sorry, u bar plus u tilde. This is barotropic, and the barotropic is nothing but the z average, and baroclinic is the difference, the fluctuation. So this system will be equivalent to two equations on u bar and an equation on u tilde. And sure, these two equations are not decoupled, right? And the good thing, or the main observation, is that this equation is basically 2D Euler. And this equation is Burger's type equation. And this observation that I just told you, this observation here, that it's not surprising that these two initial data are the barotropic, the baroclinic, are the baroclinic component of the velocity, right? Because if you want to look for singularity, you will not look for them in the 2D Euler equation. You will look them at the Burger's component. So this is, and we didn't know at that time. I think at least myself, I didn't know that. Okay, And by checking, so we find out that these results are indeed for the U tilde component. Okay, so this is, and also this is not surprising because in my result with the lean and TT, when we studied the effect of the rotation, so we said, we observed very clearly that the blow up of this component is prolonged when you increase the rate of the rotation. Good. Okay, so so far, if I summarize, so in the inviscid case, we have two results. So the first one, he said, if we have smooth solution to specific initial data, then we do have singularity formation. And the second one, it's you can construct explicit initial data, but something happens. Either the L infinity norm blows up, or the acceleration, or the x derivative along the trajectory. Okay, so before going to the new results, so I want to mention that the same W equation, the blue equation that that we reduced here using the symmetries. So it's the same one as for Wong, actually. It's exactly the same equation. I want to say that we can recover it using other reduction. Okay. For instance, if you look to solutions to the primitive equation in this form, then you can solve for the pressure again, and then you can obtain this red equation, this reduced equation. And this red equation is nothing but the blue equation, exactly the blue equation where you set WZ to be A. Okay, so we are talking about the same thing. Good. So what was the main idea? So the main idea, we said, okay, so if we look to self-similar using the scaling, you change W by lambda W, there is only one scaling. It's a 1 over 1 minus T. That's quite rigid. Okay. So we said, okay, let's look for if we can find a regime in which this pressure term is negligible. Remember that this term is exactly the pressure term. Okay. So it's just a guess. So let's see if we can find a regime in which this term, the pressure term, is negligible somehow. Okay, we don't know yet. So this red equation now becomes this simple transport equation with a non-local transport equation, right? And we relax the domain from 0, 1 to 0, infinity. I'll tell you why. Okay. Now we have much more richer family of scaling. So this new red equation now enjoys 2-parameter family of scaling. Okay, so these are the scalings. So you can change, you can rescale A by 1 over lambda, and the X with 1 over lambda also, and you can rescale time with another parameter mu. Okay, and now this 2-parameter family of scaling makes us suggest the following answers. Okay, so let's try to look for a solution that has this shape. So in other words, we have chosen lambda mu to be 1 over T minus T, and lambda T minus T to the power beta. Okay, so instead of working with lambda and mu, work with the T minus T and beta. Okay. So this leads us to this profile equation, a new profile equation, okay, which is this equation 20. Okay, and now let's go back to our heuristic here, okay, this heuristic. Let's go back to it and see whether this term can be negligible or not, or when this term is negligible and when it's not, okay? So let's calculate the L2 norm of this ansatz here. We calculate the L2 norm of, calculate this term, the pressure term, and then we calculate A square, okay? And we compare. So A square will be like T minus T over, over 2. And the pressure term will scale like T minus T to the power minus 2 plus beta. Remember, beta is this parameter here. So this heuristic tells us that this is a very good ansatz if beta is positive, right? Because if beta is positive, this is much smaller than this one. And that makes this approximation, that would make this approximation good. Okay. So we will call this case where the pressure term is negligible, we call it non-smooth case subcritical. We'll see why. Now, when beta is 0, then this heuristic it falls down, and then the two terms, the pressure term and A square, they balance each other. Okay, so we will call this a smooth and critical case. Okay, so what is our first result? If we focus on this profile equation, then this profile equation you can construct for any given beta positive, you can construct profiles that are continuous up to the boundary, same infinity inside, they are smooth except at the boundary, and at the boundary they have this C alpha regularity. Okay, and they decay at infinity. Now, if you take beta to be 0 in this profile equation, then you end up with an explicit solution. And this explicit solution is exponential minus z. Nothing to hope better than this. Okay? And this is one thing. The other thing, if you are looking for a bounded solution to this profile equation, then it has to be a rescale of one of these phi beta. Okay, so it has to be the rescale of one of these phi beta or constant, and the only constants are 0 and 1. Good. So now we have constructed profiles. Now, what are we going to do with these profiles? Okay, so we need to make this heuristic. We need to make this heuristic in work, and then we need to show the stability, right? But at least this is a very good starting point. Okay, so these are the two main results with Charles-Collot and Chuan-Li. So the first one is about smooth blowup, or the critical case. So if you fix this profile exponential minus z, then basically you can tune your initial data of a rescaled of this profile with the perturbation, and this perturbation is initially small in the C2 norm. Okay, so if you tune your initial data in that way, then the corresponding solution blows up at this speed, 1 over t minus t, and it blows up at z equal to 0 only. Okay, so it blows up at the boundary. And you have nu, so nu is 1 over log t minus t, and we can control the error at later time. Okay, close to the blow-up time. So if you divide this by t minus t, then the speed is like 1 over log. Okay, so this is the smooth case. So a few remarks here. So if you remember this equation, the blue equation or the red equation, right? Not this one. This is an intermediate equation. So this one, the blue or the red are the same, and they have been derived from the primitive equation, either using working in this class of solutions or using the symmetries that I mentioned earlier. Okay. So if you go back, so this tells us about the 2D primitive equation is that this quantity at the axis, x equal to 0, when you restrict it to x equal to 0, then this blows up. And this indicates formation of shock. And the shock, it happens exactly at the point 0, 0, at the boundary. Okay. The second observation, remember in the heuristic, this was the critical case in which a squared and the pressure term, they were balanced. Okay. Even though they are of the same order, but we show that the pressure is somehow lower order. Okay. And indeed, so this parameter, this scaling parameters, lambda and mu, this is lambda and mu here. So we write the differential equations for these. Okay, we follow the dynamics. So the dynamic of these parameters, scaling parameter, they look like this. So lambda t, the time derivative is -1 plus some constant that depends on the pressure. Okay, times nu. So lambda is basically t minus t, right? And then nu, because of this pressure term, it has this log law. Okay. So we see that how the pressure is responsible for this log correction. And in some sense, the pressure slows down the blow up when we compare it to the subcritical case. So the pressure is not an enemy. And it was nice to see this on quite explicit example, basically. Okay, let me comment when we compare this result to sister equation, which is the viscous Prandtl equation. So the viscous Prandtl equation, we can do similar reduction on the axis x equal to 0, and the resulting PD looks like 28. And if you observe this PD, it's exactly very similar to the primitive equation. However, there are main differences. So the first difference is the domain. So in the primitive equation, in the Prandtl equation, the domain is half space, right? It's not, the domain is not confined. The second thing is the boundary condition. The boundary condition for the Prandtl equation is Dirichlet, right? And Dirichlet automatically rules out any kind of blow up at the boundary. Okay. The second thing, the second observation or comparison with respect to Prandtl is that because we have the viscosity here, so there is a large scale that appears, and we show that the blow up in the case of Prandtl, the blow up happens at infinity, goes to infinity. Okay, so this is the larger scale that happens because of the viscosity. So this was a result with the Roule, Collot, and Masmoudi. Okay, and as I said, so the blow up for Prandtl cannot happen at the boundary, whereas for the primitive equation, it happens really at the boundary z equal to 0. Good. So the reason why this blow up for Prandtl goes to infinity is to preserve the incompressibility. So for the primitive equation, we have the pressure term. It's annoying in terms of analysis, but it's helping to preserve the divergence-free condition, the incompressibility condition. Whereas for Prandtl, we don't have the pressure. So to maintain the incompressibility, the blow-up point has to go to infinity. Okay. Good. So now the second main result is in the non-smooth case. So now we are talking about beta greater than 0. And remember, when beta was greater than 0, then the heuristic was like the pressure term is lower order term, it's negligible. Okay. you can neglect it. And basically that's true. So in this case, if you take phi beta profile, so as I said, it has this C alpha regularity, and it's C infinity inside, decreasing, nice function. Then again, if you tune your initial data, okay, with the perturbation, with the rescaled profile, appropriate rescale of the profile, and initial perturbation that it's not large, it's small, then the corresponding solution blows up at this speed, and the parameter nu, it's t minus t to the power beta, okay, up to some factor mu tilde. And we do have control of the solution, the error, sorry, a tilde is the error. Good. So a few remarks as for the previous theorem. So the first one is this nu tilde parameter is to that will determine the exact profile. Remember, if we have a profile phi beta, then if you rescale it, you get another profile for the same beta. Okay, so the tilde is to fix the profile. So this type of results have been applied for several equations. I already mentioned Prandtl equation, and the specificity that you start from initial data that has soft singularity like C alpha, and you propagate it to the solution. This is a hyperbolic feature, okay? And it was applied to burgers by Kolo, Roule, and Masmoudi. It has been applied for wave equation by Krieger, and for Euler by Tarek El-Gendi and Roule, El-Gendi, and Masmoudi. Whereas for the smooth initial data, like our first theorem, it was the profile was smooth, so there is no singularity in the profile. This question still remain open for the 3D Euler equations, for instance. Okay, now if you look to this regime, in this subcritical regime, and you look for the dynamic of this scaling parameter, now you see the difference with respect to beta equal to 0. Okay, so lambda t is -1 plus higher order terms, and lambda is basically t minus t, right? However, nu t here, the dynamic of nu, you have this new term that pops up when beta is non-zero. Okay, and this, because of this term that is related to the pressure, right? Because of this dynamic, so nu t, it's like t minus t to some power beta. It's not log when beta was 0. And that was the conclusion that that the pressure slows down. The pressure is not an enemy. It slows down the blow up speed. Okay, how much time do I have? Sorry.
Another 5 minutes or so.
5 minutes. Okay, I hope, yeah. Okay, any questions so far? So let me make here. I'll start to give you the elements of the proof. So first of all, we want to construct the profile, and basically this is the equation of the profile, right? And we see that this is a second order differential equation, and it's non-autonomous, particularly when beta is non-zero, right? So this is non-autonomous, but we can make it autonomous by changing variables. So if we set psi to be this speed here, then we can rewrite this equation into this system, and we can basically do phase space analysis. Okay, so we can draw the vector field, right? And we have two null lines, so phi equal to 0, phi equal to 1. These are these two lines, and the flow here it's ascending. Okay, so this psi equal to 0 is not allowed. This speed does not never vanish. You can solve that. If it's 0, then you get an absurdity. So this does not vanish except at these 2 points, and these correspond to the constant solutions phi equal to 0 and phi equals to 1. And these are the only constant solutions. So once you draw the phase space, then you can split the phase space into regions. So this is the first one, Z1 plus, Z2, Z3, and the negative corresponding part. And our target was looking for bounded solutions, okay? And the bounded solutions, we found them only in this region. If you assume that you have a bounded solution here, you get a contradiction. If you assume it here, you get a contradiction for different reasons. Probably I won't have time to do that. Okay, so this is about the construction of the profiles. Now, to do the asymptotics, so we needed the asymptotics of this profile at z equal to 0 to see the singularity, and at z equals to infinity to investigate the rate of decay of the solution. And that was really important for the analysis that will come. So for this asymptotic part, so we basically straighten the velocity. So we start with this equation. You see that the velocity here, it's quite complicated. So what do? We straighten it, okay? So instead of working with this equation, we will set the velocity to be xc, okay? In other words, we do change of variables, this change of variable, that will make the velocity to be xc. And once we have this equation, the solution to this equation is quite explicit if you fix some initial condition, okay? So the solution of this is explicit. This is the change of variable. Then we transfer this information on H to the corresponding information on phi. And we get exactly the, sorry. Why it's not, oops. So we get this, the asymptotics here. I don't know why. Yeah, okay. Good. Now, I think I'm running out of time. I'm really sorry. So the second part is to study the stability of this blowup. So we take A and we rescale it in this form. So lambda is the speed, and nu is the spatial scale. So the equation on A leads an equation on B, and this is the equation on B. And then we perturb B around this profile phi plus some perturbation epsilon, right? And we write down the equation on epsilon, this perturbation, this error term, okay? So we write down the equation on epsilon and epsilon z, the z derivative of epsilon. So we get these two PDEs. And then we impose boundary conditions, okay? So we impose boundary conditions, so epsilon vanishes at z equal to 0, as well as its derivative that vanishes at this specific order, okay? So this specific order is dictated by the decay of the profile phi, okay, that I mentioned earlier, okay? Once we fix these two boundary conditions, then what we get, this will automatically give us how the dynamic of these scaling parameters will be. So lambda s plus 1 is basically this, okay? And nu s over nu is basically this, plus a term coming from the pressure, okay? And now we split the analysis into two regions. So we take the interior region, we fix some z star. Z star is a fixed parameter that we will fix at the end of the analysis. Then we fix this star. Then we study this interior region, z between 0 and z star. And then we study the region at infinity, or the exterior region, when z is bigger than z star, less than 1 over nu. And we measure the error in two different norms, depending on the region. So the first one is weighted Sobolev. So we take the z derivative of the error, square it, and with the weight w. And the second region, we measure it with the N infinity norm. And because of the weight, our choice, specific choice of the weight, then these estimating E1 and E2 in the interior exterior, that gives us estimate of the N infinity norm in the whole domain. Okay, so in the interior region, so we will construct Lyapunov functional by suitably choosing the weight W. Okay, and in the region, in the exterior region, so we will apply a maximum principle, and we will use the decay of the profile as well as the property of the flow that is outgoing. The flow is going from region A to region B. It's not going backward. Okay, so it's going from the bottom to the top. If you think as Z for the Z vertical variable. Okay, so the whole proof goes like by bootstrap argument. So we choose our initial data to be close to the blowup. So this is the initial closeness, and then we assume that the solution stays trapped close to the blowup for some time S0, S1. And then the goal is to show that we can choose S0 large enough so that S1 will be infinite. Okay. I think I will have to stop here. Yeah, probably it's a good time to stop. Over time, I think. Thank you very much.
Question, comments? Chat. Well, if there is any question from the virtual audience, just please unmute yourself. Let me start asking a question. So how does, I mean, I agree that this is post-Prandtl as well, but what's the connection with this scenario for Euler in the somehow approach? They also have, you know, blow up at the boundary, which looks almost like a shock as well.
Yeah, is it? But the initial data, I think it's non-smooth, right? I mean, yeah, the profile. The profile is non-smooth, right?
I think it is.
So whose result is this?
Well, it's not a I mean, it's a scenario. I mean, it's not
Scenario.
a
Oh, I see. Yeah, yeah. Oh, that would be great. I mean, yeah. And the profile, there is a profile, or?
It's an axis in the axisymmetric set.
The case.
But some of the features of what you are describing sort of reminds me. I mean, their study is numerical, but
I see. Yeah. I think that's a good way to go. Yeah, I think that's a good, reasonable way. Yeah. I have a student. She was working on the axisymmetric primitive equation, and yeah, she showed like the blow up happens at the boundary, right? Yeah.
Any further comments or questions? Well, if not, let's next stream again.
Thank you very much, Anna. Thank you all for coming, and hope to see you sometime soon.
Yeah, likewise. Thanks, Liam.
Thank you. Have a good evening.
Thanks. There's no stops.